This is still our last lesson, 2-9, I believe, yeah. And what we're going to talk about today are distance or motion problems involving two or more, no, just two. Let's just do two moving objects. Today's date is 12/15. So, distant motion problems involving two moving objects. Okay, now, one of the key ingredients to being able to solve these problems is you've got to visualize what's going on, and you have to use logic. So you have to ask yourself questions, and what I'm kind of getting a sense is that you guys are memorizing or trying to memorize a process, and you're not just thinking about what it's saying. I, again, saw that on your quizzes with the consecutive odd integers where you guys like, I have to memorize this and I don't remember it. Well, you don't have to memorize it, you just think it out, okay? So in our motion problems, we're going to be using the distance formula again, d equals rt. And this formula actually is going to be heading up our chart. Because in most of these types of problems, you're being told a rate, you could be told a time, you could be told a distance. One of those things is going to be missing for one of the people. So taking a picture, drawing a picture of it is going to help you understand how to write your equation. Your chart is going to help you organize your data. Because in the last problems, you really had a rate and a time, and you figured out, or you had a distance and a time, and you figured out rates. And then averaging was add and divide by how many numbers you added. So there wasn't really a need for a chart. I guess you could have done a chart if you did, first leg, second leg, third leg of whatever the event was. So in distance problems involving two objects, we have different scenarios of how we're going to set up the problem. Stereotypical is that you have two objects that start from the same location, but they go in opposite directions. So we're going to write down start together, go opposite directions. So it would be something like this. And information is you're going to be given maybe a rate for this guy and maybe a time for him. And you may have a rate for this guy and a time for him. So those little numbers are just signifying that one goes to one guy and the twos represent the second guy, okay? And they're generally what they're going to ask is something about what is this particular distance, or how long is it going to be before they're this particular distance apart. So generally speaking, the two objects that are leaving aren't traveling at the same rate. You might have like a freight train versus a passenger train. So always somebody is traveling faster. So what does that tell you about the distance that that guy can cover in the same amount of time that the second guy is traveling? So if you got a faster guy and a slow guy, what do you know about their distances?
Time's going to be different.
Time's going to be the same because they're going to ask you something after a certain length of time.
Oh.
Okay, the distance would be the same, right? The faster guy is going to get farther, right? That's just naturally how it goes. So we know that the faster guy, let's do it this way. If we say that this guy, R2, is faster than this guy, if time is the same, so if time 1 is equal to time 2, then what we can conclude from that is that the distance the second guy travels has to be greater than the distance the first guy travels. I mean, that's just logic. Okay? So together, though, they would give you that big distance. All right? So to put an equation together, you might say the distance of the first guy plus the distance of the second guy is going to end up being this grand total distance. Okay? So we may come up with an equation that would say distance of one plus the distance of the second guy would have to be equal to the total distance traveled. So that's a scenario that we tend to see. Start together, but they go in opposite directions. A lot of times this is planes. Start at the airport, one goes east, one goes west. Same thing with trains. When you hear east and west, north and south, you know it's one of these types of problems, okay? Another problem, another scenario would be start the same place, same would be this way, but at different times. The question becomes, when are they going to be at the same location? So that kind of is weird. How can somebody leave after somebody else but then catch up to them? What would have to be true about the second person if they left later but they were able to get to the same location as the first guy? Okay, Liam? Yeah, so you got a guy who's traveling faster. He can catch up with the slower guy. We did a question on a Math 8 test where we had two guys that were both trying to gain weight. One guy was gaining twice the amount of weight that the other guy was, and there came a point where even though the first guy was heavier to begin with, the skinnier guy, because he was gaining twice as much weight every week, they got to the point where they weighed the same amount of money, and then the skinnier guy would actually weigh more than the fatter guy, okay? And it's all because of the rate at which the weight was being gained, okay? So it's going to look something like this, where you've got, this would be your first person, and this would be the second person. That's how it kind of begins. But eventually, they're going to be at the end the same place. So if we've got R1, so he has some sort of rate, he has some sort of time, so he's, goes, okay? What happens with the second guy is that he's going at whatever his rate is, but his time is going to be different. So our two scenarios, in order for us to end up with the same distance, would be that the first guy's time would end up being greater than the second guy's time. But to make up for starting later, the second guy's rate would have to be more than the first guy's rate. The bottom line is that their distances eventually would be the same. And that's how I would write my equation. I would set them equal to each other, okay? Let's see, what's another scenario that we tend to see? So we have them going opposite directions, we have them starting the same place, but at different times. No, we would never have rates that are the same, not on these. So the third scenario that I can think of that I see is they start in opposite locations, but end at the same place. So the picture looks like this. Now, it's not going to be a head-on collision, and we're going to have death ensuing from these types of problems, but they're just basically, like, two people are coming from opposite directions, and they're going to meet up at the park. Okay, so one person's from their house, the other person from their house, and they're going to meet up at the park. Now, this is very similar to the other one in that the time would be the same for these two, but it's going to be differences for the rates. Because you always have rates that are different. So one's actually going to be traveling farther than the other one. It's the same idea as them doing this as well, but I've also seen problems where they're doing this.
So like one lives farther away from the airport than closer?
Exactly. Okay, but because one's traveling faster, he's going to get there at the same, the time is going to be the same when they meet.
Like how they used to.
Right, right. So tend to have one guy, we'll just say R2 has a greater rate than the other guy. So you got to have somebody's got a greater rate than the other. Okay. And generally, again, in these problems, you may have the time is the same, you may have the time is different, just kind of deals with it. But again, this is that same scenario that these two guys aren't going to travel the same distance because of the rate is going to be different. So let's make, I would say time would be the same on these again. And then we would have the distance of the first guy plus the distance of the second guy would be how far apart they are to begin with. And I'd say at beginning. So two people that are 15 miles apart agree to meet at the park in an hour. If this guy goes this fast and that guy goes that fast, blah, 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 blah. Because they together are they're not traveling the same distance. So, but they're 10 miles apart. So we know how far apart they are, but they come together. So how long would it take for them to meet or whatever it was, okay? So again, how we're going to do charts on this, a chart is very helpful to organize. So let's say we were dealing with cars. Color code. So generically, you would have something like this. Car 1, car 2, and then here's where your titles change. We use the formula. Rate, time, distance. And again, to get the third column, you would multiply the first two columns. Okay, and then to create our equation, we're generally picking information from here, from the last column. This info creates the equation. But again, the equation is different based on the scenario of the problem. Okay, so let's do a couple of setups. And again, I'm going to tell you the book loves to do ugly things. So what we're going to do is write down a problem, come up with our chart, write our equation. Okay? And then I'll give you answers and you can work them out. Okay? So this may end up taking us 2 full pages to get through all of this. So directions, we're going to tell us to solve. So let's start one. 2 trains are 550 miles apart, heading towards each other. So this is like that third scenario we just talked about. On parallel tracks. So they always tell us this piece, and why do they have to tell us they're on parallel tracks? So they're not going to be crashing into each other. So they're just trying to give you a little peace of mind that there's not going to be death at the end of this problem, okay? But that's what they say. Now, you guys probably don't have a heck of a lot of experience with trains. I lived in Switzerland, and trains was the mode of transportation everybody took. So there's a lot of tracks. Train A is traveling east at 35 miles per hour. while train B travels west at 45 miles per hour. When will the trains pass each other? Now, here's what they're actually telling you to solve for. What's the precise amount of time that those trains are right, they're nose to nose, but on parallel tracks? Not when have they gone past them, okay? I know it sounds like they've gone past, but what they're saying is when do they actually arrive so that they're at the same exact point, each of their fronts, okay? So it's not like you don't know how much they've crossed over. They're right touching each other. So picture-wise, you've got one train going this direction. You've got the other train going this direction. Now, what do I know? I'm so bad with east and west. Let's see, east would go to the right, west would go to the left. Is that correct?
Never eat saw you walk.
I know that part, but I just doesn't. I'm very bright, but certain things I'm stupid in, and this is my stupid area. I get discombobulated every time I try to think about this. So train A is traveling east. So he's going at a rate of 35 miles per hour. So I'm just going to use the number for right now. This is train B. He's heading west, and what we know is his rate is 45 miles per hour. They've both started at the same time. Once they're exactly 550 miles apart, that's when the timer starts going. So the timer stops when they're here. So in other words, they both are going to, like this. Okay, notice they're not crashing. They're right at each other, but not, okay. Their time would be the same. Okay, because they both are starting when they're exactly 550 apart. So the time on this guy is our x value. And the time on this guy is our x value. Now, they mentioned that the trains were 550 miles apart. So what we're going to do is we're going to create an equation that says the distance for train A plus the distance of train B has to cover that 550 miles. So that's what our equation is going to be. We're going to use distance for the train A plus the distance of the train B would be equal to this total distance, the 550 miles. Okay, so I'm going to create my chart real quickly. So we've got train A, train B, A, B, helps if I write it in when I say it. And my top is the same. So train A we said was 35, time is x. Actually, let's color code here, sorry. 35x, and the distance it travels is 35x. And then train B is going 45 miles per hour at X amount of time, and its total distance is 45x. So these are the distances that we're going to use in our equation. Here's train B's distance. Here's train A's distance. So my equation is 35x plus 45x equals 550. Okay? And then you could solve that. You got combine like terms, divide both sides by, what is it going to be, 80, and solve it out. Time isn't always a whole number. Sometimes it's a mixed number. Okay? Let's do another one. So let me just think, there's a good one here. So a second scenario would be one train leaves Kansas City, traveling due east at 45 miles per hour. A second train leaves 3 hours later from Kansas City, so from the same place, traveling due west at 60 miles per hour. When are they 870 miles apart? So we're leaving Kansas City. So here's Kansas City. And one is going east at a rate of 45 miles per hour. We have a second train that's going due west 3 hours later. I'll get to that in a minute. And his rate is 60 miles per hour. Okay? So the first train to leave, we don't know what its time is, so we'll just let it be X. But the second train, if he's leaving 3 hours later than the first train, how would we represent his time? If the first guy's time is X, and our second guy's leaving 3 hours after he left. Is he traveling more time? Is he traveling less time? No, this is not a shrug shoulder thing. This is pretty straightforward. Joy?
X minus 3.
Yeah, he's going less time. And what allows him to travel less time? Look at his rate, 60, versus the other guy's rate of 45. So the faster guy can travel less time to meet a goal than the slower guy. Kind of how it works out. They gave us one number, and that was, when are they going to be this far apart? So what I have to do is figure out the distance that one guy goes, and I need to figure out the distance that the second guy goes, and then that's going to get equal to that 870. So how I can write this is, you can say eastbound train, westbound train, first train, later train, whatever you want to do, fast train, slow train, a lot of different ways to describe it, but train, not good enough. So I'm just going to call it first train, second train. The top is the same rate, time, distance. So the rate of the first train, it was 45, his time was X, his distance is 45X. Okay? The second train, his rate was 60, his time is 3 hours less, and then, sorry, I kind of crammed myself a room here. His distance would be 60 minus 3x. So I'm going to take these two values here, and they get substituted into their appropriate location. So here's his distance, and here's his distance. So my equation is 45x plus 60 times the quantity x minus 3 equals 870. And then I solved that one out.